Hello, today we're going to discuss Chapter 4.1 for Honors Chemistry, which is about the new atomic model and the electrons. So we have a couple of things to learn about light because electrons behave like light in that they have a wave property to them. So we need to know what is electromagnetic radiation. Electromagnetic radiation is a form of energy that travels in waves at the speed of light. Some things that you guys might have heard of are microwaves, radio waves, X-rays, and gamma rays. Those are all types of electromagnetic radiation. The electromagnetic spectrum is all of the forms of radiation from low energy to high energy or vice versa. And it's in your book on page 98. So if we go to the textbook, page 98, we have this picture. You are supposed to copy just the gray section, not this green and pink part down here, but just the gray, listing the types of radiation. Your book lists them from highest energy to lowest energy. I prefer to do the opposite, but it really doesn't matter as long as they are in the correct order. So this is showing us that gamma rays, that's the Greek letter gamma, is the highest energy or the shortest wavelength. We'll talk about that in a second. And then long waves, which are related to or close to radio waves, have the lowest energy and have the longest wavelength. And then we have this tiny section here, which represents the visible spectrum. So these are the only colors that we can see. And it goes from shortest wavelength, which is 400 nanometers or violet, to the longest wavelength, which is low energy, our red light over here at 700 nanometers. So this is the section that we see. Next, we have two key terms that we need to know. So we need to know what a wavelength is and what frequency is. And we also need to know the letters that we use to designate wavelength and frequency. So this is the Greek letter lambda, kind of looks like an upside down Y, so lambda. And then here we have the Greek letter nu, N-U, which is like a V italicized, but it's slightly different. So wavelength is going to be the distance between the crest on two adjacent waves. So if I were to draw the wave right here, the distance between two adjacent crests is the wavelength. And so that would be a longer wavelength and a shorter wavelength. Might look something like this. Okay, so we can measure from crest to crest, or we could even measure from trough to trough. We should find the same wavelength for both. The frequency is the number of waves that pass by in a second. So for a longer wavelength, if we were timing this traveling past us, we might have 2 of these waves pass per second. So we would say the frequency of that would be 2 waves per second. This unit we also call hertz. Okay, you guys might have heard of that. So that would be 2 hertz. If this is traveling at the exact same speed, which they are all traveling at the speed of light, which is the same, then we might have 4 of these pass by per second. So the frequency of this shorter wavelength might be 4 cycles or waves per second, which we can write that as 4 hertz. Okay, so that's wavelength and frequency. What I want you guys to know is that the longer the wavelength up here, the longer the wavelength, the lower the frequency, and vice versa. The shorter the wavelength, the higher the frequency. Okay, these are a little bit different than energy. So let's relate the wavelength to the energy. Here we're talking about frequency. I'm going to ignore this for a minute. What I want you guys to know is that the long wavelength that we saw up above, the long wavelength, which had a lower frequency, represents lower energy. So a longer wavelength, like we drew up here, or if we were to go back to our book, the long wavelengths correspond to low energy. And the shortest wavelengths, so a short wavelength, would mean a high frequency, but more importantly, I want you to think short wavelength equals high energy. So think about those gamma rays that have so much energy that they can destroy our cells and our organs, and they're very dangerous. They have the shortest wavelength of them all. Okay, they're very tiny and they have super high energy, which makes them incredibly dangerous. All right, we do have this equation that we can use to calculate frequency or wavelength using the speed of light, which is a constant. It's 3.0 times 10 to the 8th power. We're not going to actually calculate with this, but it's a very simple algebra equation. Okay, and here are our symbols one more time. This is lambda, which is the wavelength, and nu, which is frequency. I'm going to skip over photoelectric effect. If you want to read it, it's in your book. So what we need to know is a quantum. A quantum is a specific amount of energy that can be lost or gained by an atom. So we talked about if you throw a ball from point A to point B, the trajectory might look something like this. Okay, it's going to follow a path from A to B. An electron will pass from A to B by leaving A and appearing at B and never being in between. So the difference between these two energies is known as a quantum. It's the amount of energy that can be gained or lost as the electron moves from one to the other. Okay, so it's a distinct amount. There is no in between for electrons. And if we wanted to calculate the energy of that transition, let's say it went from energy level 1 to energy level 2, the difference between them, that energy, would equal h, which is another constant. It's Planck's constant. It's a very big number, times the frequency of that. So, for example, if it were to go up in energy, so it's moving up from 1 to 2, it had to gain a certain frequency of energy. And if we multiply it by Planck's constant, we will calculate the energy that it gained. Okay, again, you probably will not be asked to calculate a specific energy, but it's just this simple equation. Planck's constant times the frequency, and it tells you how much energy was gained or lost by that electron. A photon is a particle of light having zero mass and carrying that quantum of energy. So a photon is a very strange thing. Electrons are particles that act like waves. Photons are waves that act like particles. So this is my light that is going to be shining on my atom. And what it says is that it's going to carry these distinct quantums. So it's like a little packet. So this much energy will be delivered at a time. And then this much energy would be delivered. So they have these distinct packets or amounts of energy. And that is called a photon. So light, visible light, for example, is delivered in these little packets of quantum called photons. And lastly, we have the Bohr model of the hydrogen atom. So a Bohr model, Niels Bohr just said that the electrons go around the nucleus like the planets go around the sun. So we would have our nucleus. We cared a lot about the nucleus last chapter, and this chapter we're going to kind of ignore it. So it's just there in the center. It's very tiny. And it has all of the mass of the atom. Out here, we have the electrons that are really far away and have basically no mass, but they are really important to how the atom is going to behave. Okay, here's energy level 1, and here's energy level 2, and energy level 3 out here. So the one lonely electron in hydrogen can go in between these energy levels. If you add energy to that electron, it's going to jump up to a higher energy level. So it went from energy level 1 to energy level 3 there. And then what goes up must come down. So that excited electron is going to fall back down to what we call the ground state. That's its lowest possible energy that it can fall down to. But it could first go from energy level 3 down to energy level 2, and then make another trip from energy level 2 down to energy level 1. The reason I focus on this is because when you have a transition from energy level, so let's back up a little bit. We had first a transition from energy level 1 up to energy level 3, and it happened because the electron absorbed energy. So that's absorption. Okay, it absorbed energy and went up to a higher level. When it comes back down, this one right here is important, energy level 3 down to energy level 2, it's going to give off energy. Let's change the color here. So this is going to give off a wavelength or photon with a certain amount of energy there. And that process where it drops down and gives off light is called emission. Okay, and it doesn't have to be visible light. The wavelength that's given off corresponds to the difference in their energies. So when I go down here, this process where the photon is exciting the electron is absorption. Down here we have emission. So if you can see these different arrows, the small one that we just drew, and I drew it as a green line, so sorry to confuse you. This color that's actually going to come out, it has a wavelength that corresponds to red light. So that transition is going to give off red light. And notice that it's a small distance between 3 and 2. Over here we have a big distance. It's going from energy level 6 down to energy level 2, and the color that corresponds to that larger transition is going to be violet. So this is a high energy, and I should have drawn it a little bit closer together. So these are a shorter wavelength, right? There we go. So shorter wavelength color is given off because this is more energy. The transition was E6 all the way down, that's a 6, to E2. So the big difference between their energy levels corresponds to high energy, which is a short wavelength, which is violet. Okay, and so if you put that all together for hydrogen, this is called the emission spectrum of hydrogen. It just shows all the different wavelengths that we can see that are given off by these transitions of electrons. All right, that is it for 4.1. I hope you guys have a wonderful day.